Example 5. So it says find midspan deflection and slope at the supports of a simply supported beam of length L under uniformly distributed load Q. Assume a rectangular cross section 0.5 by 0.5 times h, and that the beam is made of steel so that G equals 0.4 E. Compare the influence of bending moment and shear force on the deflection. So let's start off with the real beam. So it's simply supported under a UDL of Q. So the deflected shape would be expected to look like that. And we could say that deflection is delta, and that slope is theta, and that slope by symmetry is also theta, since it's simply supported. And we could also say that the reaction is QL/2 at both of the supports. So let's draw the bending moment diagram. So the bending moment diagram would look something like that. And the maximum bending moment, which would be on the center, that would be QL²/8, where of course the length of the beam is L. And then let's draw the shear force diagram. The shear force diagram would look something like that, going down to there. Just following the line of the reaction, so we can see that one's going QL/2 upwards. So that value there would be QL/2, and at the other end it would also be QL/2. Okay, so that's the real beam, and let's have a look at the virtual beam. So to start off, we're just going to be concerned with calculating the deflection at the center. So we're not going to consider the rotation at this stage. We just want to work out the deflection at the center. So the system is like that, length L. Unit load 1 bar kilonewtons. Reaction would be 1/2, 1 kilonewton over 2. I'll try and forget about the bars, but sometimes I'll put them in. 1 kilonewton over 2. Bending moment diagram of the virtual system would look something like that. So since that's L/2, the maximum bending moment there is going to be L/4. So you can see I've lost the bars already. But of course that one is actually L/4 times 1 bar kilonewtons, and this one here, the shear force diagram would look something like that. So going above the line to start with, down here, going across there and going across there, and just shape that in there. And then obviously that value there is going to be, it's going to be half, and that's going to be half, and let's just leave it at half, although obviously it's half a kilonewton. So the external virtual work is going to be equal to the internal virtual work. So technically speaking, this delta minus 1 kilonewton with the bar, so the real deflection at the center multiplied by the virtual force applied at the point at which we are trying to work out the deflection, and that is going to be equal to the integral from 0 to L of m as a function of x times m bar as a function of x all over EI dx, and onto that we need to add on the deflection due to shear, so again from 0 to L, and this time the function of the shear force diagram, function of the virtual shear force diagram over GA, and that's going to be on dx. So, noting a line of symmetry, so line of symmetry, and then noting also a line of symmetry acting through there. We could just decide to do our integration from everything from x is equal to 0 to x is equal to L over 2, and multiply that by 2 because of symmetry. So let's do that. Let's take a 2 out, and then put a large brackets 1 over EI, and that will be the integral of 0 to L of mx, m as a function of x bar dx. And onto this we would add on the 1 over GA, the integral from 0 to L over 2, so that should now be L over 2 of V as a function of x times V bar as a function of x over GA dx, close bracket. So notice this 2. So we didn't have the 2, we would have to integrate from 0 to L. So let's have a look at what should be integrated. So 1 over EI, and we can have a look at the parabola to start with. So we know that all of that up there is a parabola, so we can draw the parabola like there, and then we need to multiply the area of the parabola by the value at the centroid of the parabola, which is going to be that distance there. So, and if we did that, then of course we don't need the integrals. So let's work out the area of the parabola. If we look at the sheets given in appendix, so if we look at the sheet in appendix 2, there's a picture of a parabola, and it says the centroid of the parabola from the tip is going to be 5 times the length of the parabola divided by 8. So I'm going to call the whole thing as the length. just to avoid any confusion between length and L. So that pinpoints so that would be 3/8 times length. So that pinpoints the centroid of the parabola. So now we want to know, well, we can see our parabola is of a reverse shape. So from that end of the parabola, that's going to be 3/8 times L/2, because the length of the beam is L and we're only looking at half the beam, and that distance there is L/2. So we've got our position of the parabola, 3/8 times L/2, and then looking again at the sheets, we have the area of the parabola. So back to Appendix 2, the area of the parabola is equal to the length of the parabola multiplied by the height of the parabola times n over n plus 1. Now, for a parabola, we know that n is equal to 2 because it's a second degree polynomial, so n is equal to 2, so that n is equal to 2. That n is equal to 2. The length of the parabola again is our L/2, and then the height of the parabola, in this case here, it's going to be QL²/8. So, just simplifying that, the area is going to be L/2 times QL²/8 times 2 divided by 2 plus 1, which is going to be 3. So the 2's are going to cancel each other out, and that's going to be QL³ / 24 is going to be the area of the parabola. Now, we know that the virtual bending moment diagram has a magnitude of L/4, so that value there is going to be L/4, and of course the L/4 comes from up here, so that is going to be that L/4. So we want to know that value there, because the integral is going to be the area of the parabola times the value at the position of the centroid of the parabola on the axis of the bending moment diagram of the virtual caused by the virtual force. So let's do it up here as it may be a bit clearer. So let's say by similar triangles, so we want to know what that value is, so it's L/4 at the center. So we are at a distance of 3/8 times L/2. No, sorry, so we're at a, sorry, that should be 5/8, and it's got nothing to do with the L/2. It's just 5/8 of the length of the parabola. So the value down there of the maximum is L/4. So that value at that point there should be L/4 scaled by 5/8. So the integral therefore becomes equals 2 times 1 over EI times the area of the parabola, which is QL cubed over 24, which you've just calculated, minus this so multiplied by L over 4 multiplied by 5 over 8, and because it's L over 4 ratioed by 5 over 8 because that's the value which it would be at the centroid of the parabola. And I'll take the liberty of just taking that 2 out again, opening of a bracket 1 over GA, and the integral from 0 to L over 2 Vx V bar x times dx. So I'll now solve that the second bit, or the shear bit, on the next page.